Welcome everyone. In this video I'm going to talk about the Peltier cooling again. I have a few videos about this topic, but I would like to provide more information because you can do many more experiments with this that I showed, and I received some questions, so I would like to try to answer those questions by this video or in this video. So what you can see here is this is an individual TEC12706 Peltier cooler. If you check the numbers, you can guess the performance. So the 12 is roughly the voltage, and the 6 at the end is roughly the maximum current that you can run through this. But if you check the datasheet of this unit, you can see that the maximum voltage is 15.4 volts and the maximum current that you can run through this is 6.4 amperes. But everything really depends on the temperature of the hot side. So how much you can cool the hot side, that will determine a lot of other properties, the cooling performance, the temperature of the cold side, and so on and so on. But we have 4 of these guys inside this unit. So along this line there are 4 of these, and what you can see here is that this blue thing is a water cooling block. So you can see the connections for the tube which should go to your water cooler. So this is the hot side of the Peltiers, and then on this heatsink, you can see it, it's an aluminum heatsink, that's the cold side. So what you do here is you cool down this part and you carry the heat, or help the transfer of the heat by moving the air through the heatsinks, through the heatsink via these 4 small fans. These are just simple 12 volt fans, and then of course the hot side of the thermoelectric component gets hot, as its name suggests. So you cool it down with the water cooling block, and you can see that this is relatively big. So I mean, 2 of my hands here. It's a relatively big block, and you can run a lot of power through it. So if you remember, then each of these blocks are roughly 60 watts performance. So this is 240 watts in total, minus the losses and the efficiency, of course. What I will present you in this video is that I will put this in a polystyrene box, a very small, roughly 2.5 liters box, and I will cool down the air in the box, and I will follow the development of the temperature via some thermocouples. So I will measure the temperature as a function of time, basically. And then I will put a glass of water also in this box. It's a very good insulated box, so I will put a glass of water and monitor the temperature of the water, and I will see how much time it takes at a given performance of this thing to cool down the cup of water. And here what you can see with the wires is that I connected 2 of these Peltiers together in parallel. So these 2 guys and these 2 guys are connected together with these banana plugs. So I soldered the wires together, and then I just put it in these banana plugs. And why? Because then I have a large enough power supply. You can check it in my other video, somewhere here there is a link. I built a power supply just for these projects, so I can run relatively large currents through that power supply, so I can pump out large currents. Yeah, and it has two sides. So one side goes two of these Peltiers, and the other side will go to the other side of the power supply. I will show you everything, and I will use a computer, CPU, GPU cooler to keep this guy roughly around room temperature. So what I will do here in this experiment, I will try to see what's the cooling performance at a given current and at a given voltage settings. And I will tell you how much time it takes to cool down some certain things, and if you try to build something, for example, a cooling box for your car or some other things, then you can try to guesstimate by using my numbers. And also I will try to show you how inefficient are these devices in for example air conditioners and stuff like that. So you don't want to use this to cool down your room because of the performance and efficiency issues of this thing. But you can use them, for example, for smaller things like microchips or cooling boxes and so on, but not for very large volumes of fluids. So now I'm going to put the camera somewhere else and show you the setup that I use for the experiment. Alright, so basically these are the components that I'm going to use here. There are some thermometers here. I built this myself and it works with K-type thermocouples. I will make a video later on, and this is just a cheap K-type thermocouple compatible thermometer. These two guys are basically the same, but this is Arduino based, so you can connect it to a computer by a USB cable, and you can monitor and log your data to your computer. And also it contains two connections, so you can measure two temperatures at the same time. And then here I already showed this to you. This is a computer CPU/GPU water cooler. It also has a small thermometer built into this flow meter here. Nothing fancy. I will fill this up with water and show it to you, and yeah, that's all. And then here, this guy is the 4 Peltier cooling block, which I showed you a few minutes ago. So now it's just built into this polystyrene lid. And then this is the cooling box. In this length is 25 centimeters and then 20 centimeters on the other side, and it's 15 centimeters deep. So in total the volume of this box is 7.5 liters. So not too much, but it's enough for a few beers or some water or some fruits or whatever you want to use it for. And then here, that guy is my power supply in a new box. Previously, when I built this, the main power supply and the DC-DC converters were in two separate boxes. So now I bought a bigger plastic enclosure and just put everything in the same box. So now it's a bit bigger, but it's more easier to handle it because everything is more nice and so on. And now it also has a switch on the back of this box, so I can switch the mains on and off. So just to summarize, what you can see on this table is that the water cooling for the Peltiers, and this is the cooling block that we will use to cool down the air, and then some objects in that cooling box, some thermometers to follow the development of the temperature as the function of the time, and then some power supply to provide some juice for the parallel connected Peltiers. So now I will assemble this and return to you with the already assembled system, and then we will start to test this thing. So just to give you an overview of the thermometers, so this is fixed to the middle of the box by some piece of wire. So one thermometer will be measuring the temperature there, and then I fixed another thermocouple which is somewhere under this set of fans, so it is touching the heatsink. So we will be using that temperature as the heatsink temperature. And then this guy here, this will tell us the temperature of the water, and we will use this number as the value of the hot side temperature. So this is the setup. So I assemble everything, and then we will move on to the test. So I assembled our system here, and what you can see here is the following. So this is my homemade thermometer here, and there are two K-type thermocouples are connected to it. The green one, which is the temp 1, is connected directly to the heatsink of the Peltier, and then we have the white one, which is the temp 2, and that is the one in the bottom of this box. And this is the temperature of the water in the water cooler. So that is basically the temperature of the hot side, and of course the green is the temperature of the cold side of the Peltier. So that's what we have there. And on this side I connected the pump and the fans for the radiator, and also I connected the fans which are placed on the heatsink of the Peltiers, so the air will be circulated in the box. And then on this side, this is a much thicker cable, we have the 4 Peltiers connected parallel to each other. So whatever current values you will see there on the screen, on this screen, you have to divide it by 4, and you will get the current on each individual Peltiers. So everything is connected parallel, because you don't want to run these things on the maximum current, because otherwise the Joule heating will overpower the Peltier cooling, and therefore you will start to warm up the cold side. So we would like to avoid that. So I think I will run around 10 amperes, which is 2.5 amperes per side or per Peltier, and we will see how cool we can get. So I just start the power supply, this guy here, and everything will be very noisy, so we will just run this thing for some time and see how we can cool down the air. So let's turn on this thing. So there is a switch on the back. So now the pump is running, and this side is not turned on, so I just increase the current and then increase the voltage and see how far we can go. So let's make it 8 amperes, which means that we are running at 2 amperes per unit and 6 volts. So we are roughly halfway on the performance chart. So now I'm planning to leave this here and let it run for a few minutes, and we will see when the first temperature up here, that's the heat sink's temperature, will reach 0. So I will be back. So now you can see that we have reached the 0 degrees temperature at the heatsink, and the temperature of the air at the bottom of this box is 10 degrees. So that's quite okay, and we haven't spent too much time on this. So as you can see that this thing can cool down your air quite quickly if you have a well insulated box. And we haven't really increased the current. As you can see, it's 8 amperes, so it's quite okay. And if we further increase the current, which I can do now, to 10 amperes, so 2.5 amperes per unit, then we can expect much lower temperatures and of course much higher speeds for cooling. So as you can see it now, the temperature of the air is going to cool slower and slower because we are closer to the heat sink's temperature. But you can also see that the heat sink is now -5.4 degrees. So it is getting colder and colder. And you can see that the water temperature is quite stable, so it is still 30 degrees. And if you see, we haven't used too much power so far, so it's 9 watt per hour. That is quite okay, so far at least. So now, as you can see, that after a little bit more than 10 minutes and at 2.5 amperes per unit, we reached 5 degrees in the box. And you usually have something like 4 or 5 degrees in your refrigerator. So I guess this temperature is pretty much fine for refrigerating anything. But you have to notice that this temperature is only the temperature of the air. So now what I will do, that I will let this thing to warm up to room temperature again, and then I will place a cup of water in this box and turn on everything. I will not move the potentiometers, so all the values will be the same as for this air, and we will see how much does it take to cool down a cup of water in the same box. So let's do that now. So this is the cup of water there, and it is 300 milliliters. So as you could see it, I put a glass of water into the box, 300 milliliters of slightly warm water. As you can see, the temperature of the water is 34 degrees, The water in the cooling system is 25.2 degrees, and also very similar to the heat sink's temperature, which is 26.5 degrees. So they are in the same range, and that is like the room temperature. So now what I'm going to do is I just flip the switch on the power supply and see what happens to the temperature. So, as it was in the previous part, 10 amperes, so 2.5 amperes per unit, 7 volts. So in total we have 70 watts power fed to the Peltiers, and we can already see that there is some change in the temperature. So what I will do now is I will check back in 10 minutes and I will see how the temperature develops in the cup of the water and in the heat sink. So let's see what happens later. Now, as you can see, the heatsink has already reached -2 degrees Celsius, but the cup of water is still about 31 degrees Celsius. So this is the difficult part for the refrigerator, is to bring down the temperature of the warm object that you put into it. So if you have a warm object like a cup of water or fruits or whatever you put into your refrigerator, it will take a lot of time to decrease the temperature of the object. This is mainly due to the fact that the heat transfer through the air is quite bad inside this box, and in general it is bad. So despite the fact that we have convection, a forceful convection, because I'm running the fans inside the box, the temperature of the water is not changing very quickly. So this is one issue. You can solve this by directly connecting the two objects, so the heat sink and the glass of water, and you provide a better heat transfer by this. Or we can further increase the power output, so the temperature on the heatsink will go lower, and then we can expect a bit more cooling performance, but it's not significant. Or we can just wait much longer. So if you wait longer, then you will be able to cool this down, but it requires certainly a lot of time. But if you place already cold objects in this, then it's not a big issue. So after running this thing for roughly half an hour, you can see that the temperature of the heat sink is about -4.5 degrees, and it's not really changing now, so we can say that that's the sort of equilibrium temperature of that part of this system. And then you can also see that the water temperature, this guy here, is around 30.7 degrees Celsius, so that is also quite stable for a while. So we can see that the hot side of this system, so the hot side of the Peltier, is not too warm. It's just a little bit above room temperature, but we have to consider the fact that we are using water cooling, so the water has a lot of heat capacity, that's one thing, and also the cooler is quite efficient because we are not pumping too much power to it or too much heat. So you can also see that the temperature of the water is now 23 degrees. So in about half an hour we could decrease the temperature by 10 degrees. But the further we want to go down, the more time it will take. So probably we have to wait several hours to make this water to 5 degrees or even less. So I will not wait, but this video can give you a rough idea about how much time you need to cool down some certain objects in your refrigerator or cooling box. And also you can see that the temperature of the cold side of this Peltier thermal element can go down to quite low temperatures. So now I'm running this at roughly 1/3 of its capacity. So instead of running it at 6 amperes, I'm running it at around 2.5 amperes per thermal element. So you can see that even at this low power they can cool down quite well, but you have to see that despite the fact that the temperature on the cold side of the Peltier is relatively low, you should see that the cooling is not that simple. And that's basically because of the fact that the heat transfer through the air is not so efficient. So yeah, but for example, if you would have another water cooling block on the other side, on the cold side of this thing, then you could cool down the liquid more easily. Maybe that can be another video where I assemble one single Peltier with 2 water cooling blocks on each side of them, and one side will be for the cooling of the hot side and the other side is the cooling of the liquid that we want to make cold. So we can see how quick we can reach, for example, 0 degrees Celsius by directly cooling the liquid. That can be another challenge.